Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hey, it's my pleasure to introduce Sangi Tin, who is a PhD from UC Berkeley, who is actually pretty well known. I think you've been here several times,
Yes.
and you got a Microsoft fellowship.
No.
No, you didn't. Oh, you should have. And has done a lot of very interesting work using FPGAs to simulate data centers, and we'll talk about that work today.
Okay. Thanks, Jim. Thanks for the introduction. So the talk runs about 50-ish minutes. Feel free to ask any questions I can answer on the line. And the topic I'm going to present is my dissertation work I've done in Berkeley with Professor Chris Asanovich and David Patterson. The topic presented is called Diablo, using FPGAs to simulate novel data center network architecture at scale. So this is the outline agenda of my talk. I'm going to briefly talk about motivations of this work. And since we're building an emulation testbed, so we treat data center as the whole computer system. So during the course of the project, we systematically look at how computer systems should be evaluated. And we have our own methodologies. And then I'm going to talk about the beef part of the talk, which is the Diablo. Stands for Datacenter-in-a-Box, low cost, and talk about implementations, talk about architectures, and then I'll show you 3 very exciting case studies we have done, and some of them you wouldn't be able to see with current tools. And finally, since this is a really long time system building project, there are lots of experience and lessons we learned. I'll talk about that, and then conclude my talk. So data center network is a very interesting topic, right? The first I want to show you is a traditional data center network architecture. This is from a Cisco's perspective. This is the traditional one, right? So this is slides took from Cisco. As you can see, data center network usually tiered architecture, right? They have multiple tiers. Down at the bottom, a rack of servers, and each rack contains roughly around like 40-ish machines, and they have top of rack switch. And further, this top of rack switch will aggregate switch people call array switch or aggregate switch, and there are multiple levels of those. And just to give you some the idea about the size of the whole network, in a typical center, usually you see like 10,000, even more machines, and plus like thousands of switches. So this is really, really large network. There's no doubt about it. So data center network infrastructure apparently is very, very important. This slide I stole from James Hamilton from Amazon. So basically, on high level, he viewed the data center network infrastructure is the SUV of the data center. This is used an analogy of the car. SUV car is really large and heavy. It's poor gas mileage. And first of all, network infrastructure are pretty expensive, right? So it accounts for third largest cost of the whole center. And more importantly, it's not about the cost. It's about supporting like applications, and supporting about data-intensive jobs, like MapReduce type of jobs. And they're so very important, right? So therefore, there are lots of people looking at this networking design space. There are some people from research side, I believe Microsoft, and also there are some people from product side, especially like from the Google's efforts and also Facebook. They're looking at like 40 gigabit, like even 100 gigabit switch designs. If you look at all of these designs, and you'll find like lots of distinct design features. Like for example, in terms of switch design, people have different packet buffer microarchitectures. Even the sizing of the buffer is completely different, right? And also some of the switch has the programmable flow table, some don't. And even in terms of the applications and the protocols people support it, they're quite different, right? Some people support the different versions of TCP and has the congestion bit support, so on and so forth. However, if you look at all of the designs, they're pretty nice. Everybody claims they have the best design, right, compared to others. But the problem is, if you look at all the work done so far, there's one problem has been largely ignored so far, which is the evaluation methodology, right? So if you look at how people evaluate their novel designs, right, there are a couple of issues, right? First of all, the scales, right? The scale of people having right now, it's way smaller than real data center network I showed you in the first slides. If you look at the experiment people done so far, typically, you will see a testbed of less than 100 nodes, right? And especially for academia, things are even worse because they don't have money. They just use less than 20 machines and put some of the virtual machines to pretend they have lots of nodes. And the second issue is about the program that people use, right? People tend to use synthetic programs or microbenchmarks. Even some people claim they want to use microbenchmark because microbenchmark can drive their switch to full, and that's a really bad assumption. But if you look at real data center application programs, what they're running is really the web search, Gmail, and like MapReduce type of things. And last is in terms of the switch design itself, right? So there are lots of networking researchers today. They're trying to use off-the-shelf switch, and unfortunately, those switches are really proprietary. There's almost nothing you can change there. For example, you couldn't actually easily change, like say, the link performance, delays, and even the sizing of the buffers. You want to change or configure the switch? Okay, good luck. Have some talk with Broadcom, sign an NDA. They will allow you to do that. It's not very easy to do it. So here I raise a really valid question. How do we really enable network architecture innovations at large scale, like an order of like thousands of nodes? It's not hundreds of nodes, without really spend lots of money building a real data center, large-scale data center infrastructure. So before I start a project, I visit a couple places, including here, and also talk to people like large corps like Microsoft, Google, and Amazon's. I ask them what kind of features you want if you want to do networking evaluations. Apparently, one common conclusion is that networking evaluations is as hard, at least as hard as evaluating other large-scale system design. So first of all, you need decent scales, right? So data center on order of tens of thousands nodes, but you need at least like a couple of thousand nodes to see really interesting phenomenon. And secondly, if you look at the real designs, right, the real thing you want to look at, like say switches, right, they're massively paralleled. If you want to run something, explore this design space, that means you really need some decent performance in your simulators. I think about large high-rated switch. They're usually 40, sometimes close to 100 ports. Think about number of flows you support and the virtual queues. Well, there are also concurrent events just per clock cycle in the thing trying to look at. And also, if you look at network itself, it's a really nanosecond time accuracy. It's really accurate. Think about the typical usage case for 10 gigabit Ethernet. Usually, transmit a 64-byte packet, right, on 10 gigabit Ethernet. It takes about 50 nanoseconds, right? So this is really comparable DRAM access. That means if you want to have a simulators or whatever, similar things, you will see lots of many fine-grained synchronizations just during the simulations. And last but not least is people really want their production software. They need extensive application logic. People are not content with the micro benchmarks at all, especially from product side. And so here's my proposal. I'm going to use FPGAs, right? So this sounds like crazy. For you who are not familiar with FPGAs, let me just give you a very brief overview about what is FPGA. This is took from digital circuit design class from Berkeley. So FPGA is a configurable, reconfigurable tiled architectures. You can see there's a interconnect, and this is a big functional block. If you zoom in this block, you'll see a structure like this. And typically, you'll have a lookup table with a fixed number of input. That will be used to implement any combinatorial logic. And to store some states in the circuit, you have a flip-flop. So people use FPGA for many things. For example, people use FPGA to build initial hardware prototypes, and people use FPGA to do ASIC design validations. You can really use this highly structured device to build a target hardware system today very easily. Okay, so my idea is trying to use FPGA a little bit different compared to people who use FPGA for compute and people who use FPGA for verification. What I did here is I built abstracted execution performance-driven models. They're performance model, but realistic enough to run the full software stack. And overall, after build system was calculated, the cost per simulated data center node is really low. It's like $12 compared to the Raspberry Pi, right? So you spend like $25. You can buy lots of those, but you still have to buy the interconnect, and there's nothing you can change there. It's just the implementation. There also, I believe, there's similar efforts. You build some like hundreds nodes testbed using atom processors in academia. Because I mentioned, like Luis Barroso from Google said, data center is really a warehouse computer. So we're gonna take the data center problem as a computer system problem, right? So we're gonna look at how people deal with this computer system evaluations, right? One common approach is computer architect uses trying to run some simulations, right? Before I start this talk, let's get familiar with the jargon terminology I would like to use. In simulation world, people often like to mention host versus target, right? So what I mean by target is the system is actually being simulated. In my case, I'm looking at the data center design, so that means there are servers and switches and network interface card. And a host, usually when talking about simulation, it means the platform on which the simulator itself runs. In our case, is FPGAs. We use FPGA to implement architecture simulators. If you're interested in software simulators, that's going to be your x86 machines, right? We actually look at many computer architecture simulators, system simulators out there. Primarily, I think there are two types major simulators. So the first one is the most popular one is based on software. Right now, we call them software architecture model execution, in short, SAME. And the second one is like our approach is use FPGAs. We call that in short FAME. We actually wrote a paper about a couple years ago, just talking about differences and why you have to do the FPGA architecture FAME style simulations to explore the design space. Why the software is bad. Okay, so first let's look at the current state of art, right? So the evaluation method is same. This is almost everyone will use it, right? So there are lots of issues with software simulators. So the number one issue is the performance. So to show you the problem, we actually look at how computer architecture the simulations in their research, right? So by doing that, we were looking at the papers published from the premier computer architecture conference, which is ISCA, a decade ago, and also all the papers people published a couple years ago. I think the data is slightly old, but I don't think there is significant change today in terms of the way that people simulate their benchmarks. So we're actually looking at how many instructions people simulate per benchmark across all the paper people publish, and also look at the complexity of target design in terms of number of CPU cores it support, and also calculate number of instruction people actually studied per core. So here's some interesting thing we found, right? Back a decade ago, like in the last millennium, right? So everybody is looking at a single core design. And people simulate around, the medium instruction people simulate per benchmark is around 267 million instructions. And going back to a few years ago, we're moving to the multi-core era. So everybody's looking at multi-core design. So the median number of cores people study is around 16 cores. And given the complexity of the system growth over the past decade, and people do simulate more instructions, like close to a billion instructions, 825 million. But if you divide by the number of cores people are looking at, this number, 100 million, is actually not going up, actually going down. Sadly, thinking about clock frequencies that people are running today, right? For the processor back a decade ago, so everybody runs a couple hundred megahertz. But this recently, processor is actually running at a couple gigahertz. If you convert this 100 million instructions to the raw wall clock time, and this is really sad, this only translates to less than 10 milliseconds. So what does that mean? That means you couldn't even simulate a typical operating system scheduling quanta, which is typically around a millisecond. And if you look at data center applications and IOs and all sorts of things, you at least has to simulate a couple hundred minutes, a few minutes to see really interesting phenomena. And also another big problem of the software simulator is people tend to build unrealistic models, right? For example, you have infinite fast CPUs, everything just consumes one clock cycle, which is very dangerous. And so therefore, we are really betting on this FPGA-based architecture emulation. Just on high level, there are simulators built on FPGAs. So not to be confused with the standard FPGA computers you see regularly, and not to be confused with FPGA-based accelerators. People are interested. So there are actually simulators, right? Architecture simulators. So when we look at the architecture simulator design, the FAME design, I actually found there are lots of distinct design features, and there are lots of dimensions, right? So we summarize like to 3 basic dimensions, right? So the first one is direct versus decoupled. Decoupled means you can actually decouple the host cycle from your target cycle you use. So for example, you can use multiple host cycle to simulate the one target cycles. And the second one is full RTL versus abstracted RTL. So for ASIC verification guide, they tend to use unmodified ASIC RTL, but in terms of FPGA simulation, you're interested in performance, you can actually use like abstracted performance RTL performance models. And so that has many FPGA-friendly structures to simplify your designs and also increase your density. And along with the decoupled timing model, and you have a much simpler design, but just take multiple FPGA cycles to simulate one target cycle. And the last feature is single-threaded versus multi-threaded hosts. And this is really crucial for me to really be able to simulate a couple thousand server nodes with switches. I'll show you what I mean by multi-threaded hosts. Think about this case, right? What we call this is like host multi-threading, by the way. So you're trying to simulate in your target, trying to simulate like 4 independent CPUs, right? One of the easiest way to build your model is you build 4 CPU pipelines, right? But that will consume like more resources. And a simple thing you can do is you build a single processor pipeline, but you put 4 hardware threads on it. You use each of the hardware threads to dedicate to simulate one of this CPUs in target. And you have a timing model so you can synchronize all the hardware threads and make sure they, in terms of simulation, they execute in parallel. So as a proof of concept, we actually built a FAME simulators, a field called RAMGold. And the goal is to simulate 64 Spark V8 core with a shared memory hierarchy. It's a really low cost. It runs on a $750 Xilinx student board. And also, it has sufficient hardware units. Say, it has hardware FPUs and MMUs. It's capable of booting Linux. And we actually compared this simulator with the state-of-the-art software simulator, which is Symix. We found it's actually 2 orders of magnitude faster. It's more efficient. And this is also the basic building block for my data center project, Diablo. So next, let's look at the data center project, right? The Diablo simulator. So on high level, what is Diablo? Right? Diablo is really a wind tunnel for the data center networks built with, of course, with FPGAs. And so the goal of Diablo is very aggressive. We're trying to simulate a tens of thousand nodes. In our prototype, we have like a couple of thousand nodes running. And each node in the system is actually running a real software stack. They are not running microbenchmarks. And also, we're looking at switch interconnect. So focusing on the switch interconnect, we'll be able to simulate a couple of hundreds, even thousands of switches with Diablo at all levels, and with enough details, architecture details, and accurate timing. So I want to point out, so in Diablo, there are real instruction executing now. We're really moving real bytes in the network. We're not sending fake pointers. So, and also Diablo is fast enough, given like say overnight, it's capable of running a scale of 100 seconds, just a few minutes. And also, we know FPGA are really hard to program, so we pre-built many runtime configurable architecture parameters for the user to modify with their control software. There's no need to do resynthesis. We can allow the user to change, say, link performance, right? Link throughput, link bandwidth, link latencies, and also even the switch buffer layout and policy, buffer dropping policy, things like that. So of course, this could be built with the FAME technology I mentioned. So there are actually 3. So I mentioned Diablo it's all about performance models, right? So there are actually 3 basic models in Diablo. The first one is the server models. It's actually built with the RAMGold simulators. So for the server models, right now we're using a very simple timing model. We're assuming it's a fixed CPI timing model, means ALU instructions take 1 cycle, and the rest of memory instruction takes fixed number of cycles. We run, it supports Spark VISA, because I should mention this is Spark certificate processor. So we run their verification suite. And it runs the full Linux. We port the Linux 2.6 there. Right now, like bringing up Linux 3.5, which is very recent. And also in terms, the second types of models we have in Diablo is the switch models, right? If you look at data center networking design, there's really 2 types of switches. The first one is circuit switching, which is more like from the research side. And the second one is more conventional. It's just like packet switching, like production data center will run. So we actually have both models. We built both models. They're abstract models, but our focus is more on the switch buffer configurations instead of the switch routings. So the switch we actually model is looking after a Cisco Nexus switch. This is Nexus 5000, and plus a Broadcom patent pointed out by Microsoft Research. And also the the last model in this Diablo is the network interface card models, because we realized that network interface card model is really crucial. So we have a very sophisticated network interface card model. The NIC model. It supports scatter-gather DMAs and zero-copy drivers, like many features you found, performance optimization features you found in the production NICs. It also supports the pulling APIs from the latest kernels. So this is not trivial. So now we have 3 models. Let's see how I map the 3 models to use the 3 models to model a real data center. Just recall on the first slide that this is the abstract view of your data center. I'm using it's like a factory or closed topology, just as an illustration. So you have 1,000 servers, like 1,000 switches, and for sure in your centers. Instead of building like thousands or like tens of thousands different FPGA bit files, I only have like 2 types of bit files. This is very modularized designs. So the first type of bit files I use is to simulate a rack of servers plus top of rack switch. So given the current chip, which is Xilinx Vertex 5, I was able to simulate 4 racks of servers plus a top of rack switch. And the second type of FPGA design is we dedicate just to simulate switch itself. We use the FPGA to simulate the monster switches, like 10,000 like a switch designs. And for aggregated switch, array switch, and data center switches. So you can really do a detailed architecture modeling there. We connect these 2 type FPGAs using high-speed SerDes links. Well, now the connection is based on the physical topology. Say you want to have a hypercube, then you just connect the FPGA in the hypercube way. So there's no restriction, just wirings. Okay, so we actually built this Diablo prototype using multiple B3 boards. This is actually developed by Berkeley and Microsoft Research. Probably have heard of it. The B board, each B3 board has a Xilinx Vertex 5 FPGAs. So 6 boards, I use like 24 FPGAs in total. So this is the photos of our cluster. And we actually populate all the boards, the maximum memory, so it has a decent memory capacity. It's 384 gigabyte DRAMs in total. But think about number of nodes we're trying to simulate, that's still not that much. It's roughly around 128 megabytes per simulated node. But we think it's kind of interesting enough to run some networking applications. We're actually working on the 2nd generation trying to solve this problem. And also, if you look at this, the bandwidth of the memory is really great, right? There are 48 DRAM DDR2 channels. So you have roughly around 180 gigabyte per second bandwidth. And each of the FPGA has this 1 gigabit, you see the yellow cable. This is a 1 gigabit links. We use this link just for the control. So you have 24 times 1 gigabit links. We have a couple of x86 servers just to drive all the boards, and which will be used for like say the consoles, right? Your console will simulate Linux and also provide some disk functionalities. And we connect these boards using sure.
So I have 2 questions. One is I noticed on the first bullet, 128 megs per node, so your workloads have to be scaled down.
So I think yes. So for the one like memcached you were looking at, it doesn't actually matter. So in terms of the workload size, yeah.
Okay.
I think this is really limited by the board design itself.
Very small working set size that you've got.
Because yes, when I talk to like some networking people, they think like if you have 100 megabytes, yeah, you can run most of interesting protocol studies. But I know for some like storage applications, you definitely need a gigabyte because just for the cache, this is very large.
If you scale it down to that size, does the software simulator get faster? Or?
Not necessary.
Okay,
Yeah.
and the other question I had is in the previous slide, you showed how you partitioned.
Yeah.
And so is this a balanced system? And if I'm a user, do I have to manually make these partitioning decisions to get good throughput from the simulator? Or
You don't have to. We just use the naive partitions like this. You don't have to worry about that too much. And I can tell you the performance of the simulator is very scalable. When we try to simulate 1,000 nodes versus 2,000 nodes, we saw zero performance loss.
I'm thinking like if I'm trying to evaluate different types of network architectures, I may have a different topology altogether.
Yes.
Right? And how I'm drawing these boxes easily may hurt me in some places.
I don't think so. Yeah. So we don't play trick with like fancy partitioning. So we just use most simplest one, most straightforward one that will still give you some performance. And also I can tell you the performance simulation bottleneck is not actually simulating the switches, it's actually simulating the server computations. So you have to optimize your server computation simulations in that case. Okay. So back to this, we actually connect this, the prototype, we actually connect all the boards using this, like you can see this 30 cables. We run our own custom protocols, 30 protocols. There are lots of those. Each link is running like 2.5 gigabit per second. We're designing a second version, which will have a passive backplane to handle all the connections. You don't need these cables. And overall, the whole system is pretty nice. It consumes only slightly over 1 kilowatts, 1.2 kilowatts. But in terms of simulation capacity, what you saw here is that beast is capable of simulating slightly over 3,000 servers. And there are also 3,000 servers and 96 racks, and there are also 96 simulated switch there. So there are think about there are 3,000 copies of Linux running there, right? Running real applications. It's very interesting. And in terms of instruction simulation throughput, the whole system can deliver roughly around 8.4 billion instructions per second. So just a little bit about the implementation, because lots of things going on there. What I'm showing you here is a die photo of the FPGAs I use to simulate rack of servers. So on high level, this is a full custom FPGA design. There's lots of hand design there. We use minimum third-party IPs, including, so the only thing we don't design ourselves is the Xilinx IPUs. And this is pretty packed and full design. So we stretch the chip to the limit. And so it's like a 90% of block RAM utilizations. And also we're closing, after placing route, closing to 95% lookup tables will be used. And keep in mind, the FPGA we use here is like 5-year-old, it's 2007 FPGAs. If you have this here, you can potentially have more pipelines there. And we're actually running the whole circuit like a 90 megahertz / 180 megahertz. This is a double pumped data path, and just make sure I have enough ports on the block RAMs. And if you look at design closely, right, there are basically 2 partitions, right? So each partition has one host DRAM controller and of 16 gigabyte DRAMs, and I have 2 RAM gold pipelines plus 2 switch pipelines there. And in terms of size of each this model, probably couldn't see. So the NIC models and switch models and processor integer pipeline is roughly the same size, and with the floating point is double the size. So you can guess if I have a larger FPGA, how much I can put there. And so this is FPGA has 4 server pipelines and 4 switch and /NIC pipelines there, and it also has a couple of sometimes like 1 to 5, 2.5 gigabit transceivers there. It depends on which type of FPGA, which type of topology you want to use. So I show you some prototype with 6B boards. Let's say, what if you want to go with a 10,000 node system, right? So there are some back of envelope calculations. If we stick with the current technology, well, it's really old, 2007, 5-year-old technology, you probably end up using end up using like 22 B boards, means 88 FPGAs. But if you look at this year, this is really promising, right? So look at the recent technology, 28 nanometer generations. In order to simulate like 10,000 CPU systems, you only probably need like 12 boards. You actually calculate the cost of the board, assuming each board costs around 5,000. We're actually doing the board design right now. The overall cost is about 120K. That's include the board cost with the DRAM cost, and the cost is split roughly half and half. And next, I'm going to show you 3 exciting case studies. Right? This is very interesting. Okay, so the first one is we took Diablo to simulate a novel circuit switching network. This is actually the work I've done with MSR on Mountain View with Chuck Thacker. I was trying to use the Diablo to simulate the initial version of his circuit switching network. Probably you're familiar with this network, just to bring back everybody up to speed. And this is a circuit switching network, works more like an ATM, and it has multiple levels of switches in its design. So during the period of 3 months, my internship there, we actually modeled all 3 levels switches, all levels of switches. And also we try to run hand-coded dry terra-sort kernels with some device drivers. We think this is very interesting because Diablo can actually capture some performance bottleneck in the early designs. For example, we found some problems in the circuit switching setup and tear down circuit. And also we think there lots of interesting things from the software perspective. Right? Chuck's design is a lossless network, and the hardware doesn't drop any packet. But what we found actually because everything handled by the processor eventually, and the software processing speed can actually lead to the packet loss. And the second case study I did is like going back to the traditional packet switching world. So I'm looking at a classic problem people call TCP incast throughput collapse issue. This problem is actually reported by CMU. They claim they found it in a real production gigabit network attached storage. Well, the setup of the problem is very simple, right? So you have this is the setup topology. You have a shared switch, and there's a shared file server, block-based file server. And also a couple of senders connect to the same switch. So when you measure the throughput, the bottleneck link, which is the link between the shared server and the shared switch, and you plot the throughput curve versus a different number of senders or receiver, whatever, number of clients. And you see a curve something like this, right? This is the throughput, and this is the number of senders. And ideally, you want to see the throughput curve is, when you increase the number of senders, gradually going up and saturate to this peak. But in reality, in practice, this is the curve you saw. And people concluded, right? So people have done network simulations using NIS tools. People try their experiment on small-scale clusters. Researchers conclude that this is caused by small switch buffers, and also TCP retransmission timeout in the kernel is too long. And so that's their conclusion. Okay. So when I look at this problem, I actually talked to a couple of people, and especially in industry side, asked them if that's a real problem. Some of them told me, well, they're pretty artificial, only happen in a specific setup. So we actually look at how the people did their experiment. We actually found this problem actually only happens under a really specific pre-setup. It's happened with a small block size, usually less than 256 kilobytes request size, and happens only on a switch with the shallow buffers. So the first thing we want to do with Diablo is to see if we recreate this setup, particular setup, can we reproduce this throughput collapse problem, right? So this is the graph. This result you see from the Diablo, from the simulation, is actually we're trying to model a gigabit switch with a shallow buffer gigabit switch, and we're trying to run the TCP incast code. I should mention, just to be fair, we're not using Berkeley code. We're using code from Stanford Networking Research Group. And this is the throughput curve you'll see. And also we try to change some configuration points in the system, say scaling up the CPU performance to see if that affects. Also change the OISys calls people use in applications. We actually didn't see a lot of difference at the gigabit level. So this is a throughput collapse, and that's what you see on a real comparable physical setup. So this is great. So we can reproduce the problem. Okay, since Diablo is really a simulator, the question we like to ask is, what if we upgrade the whole interconnect to a 10 gigabit, right? Change the switch spec and change even the server the server performance. Right? Say, what if we how the system will perform? What if we have a faster server? And also, there are lots of things you can play with, right? So you can say, recode this program, right? The original program is written using standard pthread plus socket blocking syscalls. But if you look at the most recent server applications, they are actually using a pooling versions with more responsive versions of the OISys code, which is used this called epool. And so what if we use epool, right? Because like many current services like memcached, they're actually using this versus pthread. And what if we change this and redo the same experiment and what throughput collapse we'll get, right? So here I show you a simulated 10 gigabit switch, and with a bunch of things I mentioned, like say I'm simulating 4 gigahertz servers and also versus 2 gigahertz servers. If you look at the original code, right, use the Stanford unmodified code and just change your switch, and this is the one you get, right? So you still see a throughput collapse at the very early stage, and there's not much significant difference between the 4 gigahertz and 2 gigahertz server, with 4 gigahertz slightly better, but not that much. But once you start looking at OS, right, let's change the OISys code we use. Let's change the syscode to be epool, right? You got a drastic different curve on the left-hand side. And you see the great difference between 4 gigahertz versus 2 gigahertz. And moreover, you see this like collapse on-site points, like significant shift to the right. So this is very interesting. So first, we're happy because we can reproduce this simple problem, even if people call it artificial. But second, we found once you're trying to scale up the whole system, say change your switch, your system performance bottleneck might shift to at a very different scale. And we think looking at OS implementation, even the application logic is extremely important. Like many of the current work are done with this simple problem. People just run NS2, there's no computation model, there's no OS at all. And also we think fixing the retransmission timeout timer is not really like fixing the real problem. You have to look at where the root problem the root problem the throughput collapse is. Then you start developing some methodology or some probably new system design to solve this problem. So the last one, the last case study we think is very interesting, and we actually run a modified memcached service on a really large scale setup. So we think this is exciting because it reproduces some of phenomena people saw in real large scale environment in production, and also this is probably the first time academia will be able to look at a problem like thousands of scales. And previously, I talked to people can only afford to see a couple hundred nodes from academia. But now we're moving an order magnitude better. So it's like thousands versus hundreds. So memcached, just like probably you're familiar with that, it's just like very popular distributed key value store application used by many websites, like say Facebook, Twitter, and any large website. It's a memcached basically, like this name. And actually the code we use is a modified memcached. This is not a memcached tiny or mini, whatever. This is a modified code downloaded from their site and compile on our platform compile to Spark. And the clients we use is actually coded with a middleware layer on top of libmemcached. This is the application level that will be used to handle application level retries and things like that. In terms of the workload we use, ideally we want to have the real workload, but universities we have some limited access to the logs. But Facebook actually published their workload statistic in last year's Sigmatrix. So we look at the paper and build our own workload generator and verify our own according to real Facebook data. So we think this is probably the best thing we can get. Okay, so the first thing we did with this memcached setup is to trying to validate our result at small scale, right? Large scale is pretty hard to validate, but for small scale, we can have a relative equivalent system, physical system set up and run the same experiment, same programs on both this system and see if we can get the shape of the curve right. So in our validations, what we did is we're trying to build a 16-node cluster with a 3 GHz Xeon processor, just pretty regular, with a 16-port gigabit switch. And in terms of configurations, all the 16 servers, we use 2 of them to be the memcached server, and the rest of them will be the clients. And we'll scale up the number of clients from 1 to 14, and then plot the throughput curve and latency curve, and so on and so forth. And also, memcached is a real application, right? There are lots of parameters, configuration you can just change for the server side. So what you can change here is you can actually change the protocol used, TCP versus UDP, and which is better, and also change number of worker threads of the server, say 4 threads or 8 threads. And keep in mind, the simulated server we have is a single core model running at 4 GHz with a fixed CPI timing model versus this guy. This is a different ISA and different CPU performance. We don't expect we'll get absolute number right, but we actually expecting we're getting, what we're looking at is the shape of the curve, the trend, right, at scale. So that's what we care about the most. So the first thing we look at is trying to do the validation about from the server's perspective, right? To look at the server application throughput. So this slide shows you the application throughput we measured on Diablo, which is simulated, versus the thing we really measured on the real cluster we set up. X-axis of this graph is number of clients, like 1 to 14. The y-axis is the application throughput measured from memcached to memstat interface. So it's from it's measured in kilobytes per second. So you can see under different setup, right? So Diablo can successfully reproduce the trend of the curve, and to our surprise, because it's more like I/O bounded, the absolute value is more close to the real thing. So we're happy. So now let's look at from the client side, right? So we measured for each of the client we run, we actually measure and log all requested queries. We measure the client query latencies. And we did a similar comparison graph as the previous slides. And right-hand side is a real cluster, left-hand side is the Diablo. As you can see, again, we got the trend right. So most of the core finished reasonably fast, less than 100 microseconds. The only difference is that Diablo, the setup we have here is probably slightly, the latency is slightly better than the real setup because we didn't actually calibrate our models. But I mean, if you want to do absolute value, you can definitely calibrate your model. You can get a closer curve. But in terms of the trend of the whole system, this is very good. So the next experiment is the most exciting part of the thing we have seen so far. It's actually we're taking the Diablo and really trying to study problem at large scale. Like we try and study the problem at scale up to 2,000 nodes. Since this is simulators, you can do many tricks. You can play around many hardware setup there, right? So you can simulate different interconnect. For our case, we're looking at gigabit interconnect with a regular microsecond level port latency switch. And also we look at what if we change the whole interconnect to 10 gigabit and improve our switch latency by a factor of 10, everything like throughput latency a factor of 10, what will happen to application. I know the setup is a little bit more aggressive, but show you some ideas what we can do with Diablo at the scale. And when we scale up this application and scale up this experiment, we're trying to be moderate. We're trying to maintain the server versus client configurations. So we still have 2 memcached servers per simulated rack with the rest of the clients, and want to make sure all the server load are moderate, and we don't want to push everything to the cliff. That's not where people are running today. So the server utilization we measured after simulation is roughly around 35%, and there's actually no packet loss actually mentioned when I created this experiment. Okay, so so one problem, so like a large scale is a problem people call request latency long tail, right? It's actually identify, well, Luis Barroso from Google actually talked about this problem like a couple 2 years ago in the FCRC keynote. So we're actually trying to use Diablo C. What if we can see the similar problem at large scale? So this slide actually shows you the client request latency distributions. This is the PMF graphs with x-axis is in log, is in microsecond. Y is the frequency or and also you see two types of, there are lots of, these graphs actually tell you many things, right? First, they're the result from 10 Gbps interconnect, which is the dashed line. There are also solid lines for a gigabit interconnect. And the first thing is, we actually see this throughput, the latency long tail problems. So which is, most of the queries like requests finished very quickly and on the order of 100 microseconds. But there's still some query, maybe 1% or like 1.5%, whatever, finish a lot slower than the rest of the queries, and for some reasons, right? Two order mining too slower. And also, if you look at this like gigabit switch, we actually classify the types of query into 3 categories, right? So the one is just because this is really sizable system, some of the queries just hit the local memcached server. Some may have to traverse one switch, one aggregate switch, some has to traverse 2. So we actually plot the latency distributions of all types of queries. Then you'll find that once you have a sizable system, most of the queries are actually going across your rack. It's going off the rack. So that's very common. So that's the where it dominates. So and also you'll find if you traverse more switches, and you can see this guy, and you have this peak is significantly lower than this is local. This is 1 hop, this is 2 hop, significantly lower. That means if you traverse more switches, and the variations your query will be more. And I think Luis this year he wrote a paper talking about the cost of this latency long tail. One of the observations that once you have more switches, there are more non-deterministics in your system. So they actually capture that. And another great thing is you can compare, right, the result for 10 gigabit switch versus 1 gigabit switch. Keep in mind, everything is 10x better in 10 gigabit setup. Actually does help on this latency long tail issue, and fewer requests will finish slower. But if you look at absolute value of this, the request finished by the 10 gigabit interconnect, they are not 10x better in terms of application latencies, right? This is no more than like 2x. If you again look at Luis' talk, right? He mentioned if you look at a portion of time the query latency was spent, right? It's the time you spend in the switch or in hardware only accounts for a very small portion of the overall. There are lots of the time you just spend in the OS kernel stack. And this, again, Diablo helped to identify this problem. And also, OS, networking stack, computation, again, very, very important. Okay, so since we have this excellent vehicle, right, so you can see problem at large scale. So one big question I'd like to ask, the impact of the system scale on this long tail. This is what makes the Diablos unique. So let's look at the result we have in the previous slide. You saw the PMF distribution. Now let's look at the CDF curve, right? This took one curve in previous slides. So if you Google, right, so you're not actually interested in this part where most of the query finish reasonably fast. What are you actually interested in this part? This is the tail part of the whole request. This is where it makes the whole thing more interesting in terms of revenue and anything, right? So first, let's see. Okay, let's zoom in this CDF curve a little bit, right? So, so let's zoom in this curve to answer the questions. Let's say if we have a larger system, does it hurt the latency problem or help latency long tail problem? So apparently, I'm using here this is zoom in the curve of the tail part. This is 96. This is 100. And I only use there are lots of data points. I only use one configuration because other configurations are similar. Just show you the ideas. The one I use here is 10 gigabit interconnect running with the UDP protocols. And ideally, you want this curve closer to the roof. That means fewer things falls in the tail. But if you plot this curve, zoom-in curve with 10 gigabit here, right, you see clear trend, right? So This is for 500 nodes. This is 1,000 nodes. This is for 2,000 nodes. So if you have more nodes, more servers in your system, apparently this tail problem is more obvious. So that's the first thing. Okay. So next, because academia, especially academia, they're really fond of like looking at a system just like hundreds of nodes because of physical limitations, and they try to draw some conclusion. Many people draw conclusions just with 100 nodes. And so let me ask this question. So we will draw the same questions if I give you a platform that's capable of looking at a problem like 1,000 nodes. Just let's say for this case, look at the tail. So we'll have a different conclusion, different answers if we have a larger scale system. And one very simple experiment we can perform here is say, change the protocol, software protocol we use for the servers. Like say TCP versus UDP, right? Which is better given the specific hardware setup? Which is better in terms of the minimizing the long tail, right? This is a very simple experiment we can do. So let's first look at the experiment that we've done with the gigabit, the traditional gigabit interconnect, right? So again, I'll plot this, like zoom in the curve of the CDF, and I'll keep the same coloring scheme consistent with red represents the UDP protocol, and with the blue one represent the TCP protocols. So clearly at 500 nodes, the gigabit interconnect setup, you'll see, well, UDP is definitely a better choice because this curve is closer to the roof. Now, let's move a little bit step further. Let's go look at 1,000 nodes. Well, apparently, very interesting, right? Going up to 1,000 nodes, you don't see significant difference between TCP and UDP. And with TCP, slightly better, right? Now let's move a little bit further to 2,000 nodes. This is the result for 2,000 nodes. In this case, TCP for sure outperform UDP. Okay, so I can draw a conclusion now. So TCP is better in terms of scale. But what if we change the interconnect to 10 gigabit, right? So we still have the same conclusion, like TCP is a much better choice in terms of latency, long tail. Let's redo the same experiment, right? So first, again, 500 nodes, right? Here, you can see TCP already outperformed UDP, right? So for this like 500 node setup at a 10 gigabit. Now let's go up to 1,000 nodes. Well, this time, well, your conclusion reverted. It's apparently UDP is better. Now let's move to 2,000 nodes. Let's see if UDP is still a better choice. Okay, this is the curve we got for 2,000 nodes. They're not much difference, almost the same. So this is really interesting because we think the long tail problem is really a convoluted problem. There are multiple factors contribute this issue, and it's not a linear function. So you definitely draw the answer which one is better. So there are many other, I believe there are many other things happen at scale, and Diablo is definitely capable to help that. And when we did this like large scale experiment, we also found many other interesting things at large scale. And so
for these experiments,
sure.
so you empirically see these effects.
Yeah.
So do you know why?
I have some like rough ideas. I think the problem is, like I mentioned, like there are lots of software queues in the networking stack, and the way the current networking stack is the handle is not really deterministic. So if you look at the drivers, right, you don't just look at the switch itself. There are multiple factors, I believe, but software, the wise networking stack is the big problem, right? The way they design is actually optimized for internet. It's not deterministic. It's working in the pooling mode for most of the queues. The way that the OS train the queue. So it's not like you have a packet and you will send to the software. It's really up to the OS and decide when to notify the application. So I can't tell you exactly why this happened. I believe there are more things you can do, but this is not a single caused by a single problem. It's probably multiple. It's probably a system design issue, right? So let's look at the other issues. Sure.
How much observability do you have?
How much observability? Anything you can use with the software, you can do that, and also we use hardware.
So anything you can see in a software simulation.
Yes, it's just standard. Well, this is a standard Linux. Whatever you can do with the Linux, you can do it.
But can I look into your FPGA?
Yes.
Switch and all that.
You can actually do that. We can actually generate. I actually didn't use it right now, but I can give you some distribution of the way the queue is drained over the time, and that's done through the hardware performance counters. So you can yeah, we have this like debugging infrastructure there, but now for this experiment, I just like spending my time finishing up. I didn't look at those, but yes, the answer is definitely possible. You can see more things that you couldn't see on real switch designs. Yeah. So yeah, potentially this is architecture simulators, right? You want to probe whatever you want, and also the nice thing about FPGA is the debugging infrastructure can run in parallel to the main stuff, so it has almost zero performance impact. Yeah, so that's good. Okay, so let's look at other issues, right? Other small issues. So the first issue is because Facebook, if you look at, there's a Facebook published a blog about their memcached choice, like the protocol choices, and Facebook is saying we're running the UDP. The reason for that is because UDP consume more memory. TCP consume more memory than UDP. But we actually didn't see this, right? We actually look at the server memory utilizations at scale. They're pretty much identical, right? So between two protocols. But we think what really matters is the dynamic patterns of the TCP versus UDP, right? So it could be caused, the memory consumption could be caused by the server not evenly balanced. Like you have more concurrent, more in-flight transaction you have to handle for TCP versus UDP. But you can't simply draw the conclusion TCP is definitely better. It's really about load balancing. And another thing we found is when we look at how people do, especially system networking folks, to similar experiment, they tend to focusing on the transport level protocols. Like say they're not happy with the vanilla TCP. They do lots of hacks in the transport protocol, control theory-based transport protocols. And also they're trying to hack the kernel, just say tweaking the timeout values of the protocol. But we found some cases like vanilla TCP might be just fine, right? You have to, what you really should focus is not just the protocol itself. You have to focus on the CPU processing, like the case of the TCP incast, right? You have to focus on unique designs, and also even OS application log is crucial. And also, like I mentioned, answer to Eric's question, like we think there are lots of software queues. Like when you start building the system, you know, when you start writing the driver, you figure out the way the currently the networking stack processing the packet is very, very complicated. There are lots of queues and buffers just in the software stack. It's not just like there's a buffer in the switch. There are more software buffers, which is more non-deterministic in software stack. So why don't you just get rid of these buffers, unnecessary buffers, and build a supercomputing like interconnect directly on your SerDes fabric, right? So now also we saw many other interesting, like say, we try to change the internet hierarchies. Like sometimes you have one layer, sometimes we have two layers. We found adding another layer is actually slightly affect with server host DRAM usages. I think that affects your flow dynamics. This is also very interesting to see at large scale. And so in conclusion, so we believe by looking at evaluating the data center networking architecture, anything, looking at OS application logic and computation is definitely crucial. You need that. And second thing is you can't generalize your result you got from 100 nodes, couple hundred nodes to a couple thousand nodes. You see completely different things at a couple thousand scale. And we believe Diablo is good, really good enough to generate this relative numbers versus the absolute number, because we want to figure out the trend, right? And we think this is really a great design space exploration to a large scale before you really invest, shell out like couple $1 million to build a real system. So apparently, I learned a lot during building this. They're like, this is like 8 years effort, by the way. So Diablo, you can see now, is actually designing for a large-scale system with capable of simulating thousands of instances. So there are some people who ask the question, so I'm only interested in things happening within the rack. So will Diablo still help me because it's using FPGAs, it's supposed to be slow? My answer is yes. The reason for that is because we have like 3,000 instances here on the prototype we have. You can actually potentially run your experiment in parallel. All the experiment we run so far finished overnight. think about if you have a real physical design, and when you're trying to run your experiment on real physical design, and sometimes you couldn't afford the cost of building multiple racks, but you can, you have to run your experiment in sequential, but on overall, it's not necessarily faster or significantly faster than running in a simulator. So once you have a 3,000 simulated instances, great massive simulation bandwidth, that will probably change the whole story. And the second thing is, because the goal of Diablo is very aggressive, we're actually running the real software code. It's not the microkernels like researchers use. We're trying to bring up the whole the off-the-shelf Linux kernel. So we found there are lots of issues in the software. The real software, they have bugs, right? So we actually saw very interesting things when we port Linux. Right? There, a couple of times we have to change the hardware to work around this Linux issues, right? Because we sometimes change the software and then the problem show up again, and then we need to decide, okay, we have to change the hardware to make sure we can run this legacy Linux. And also, we actually found that there's some Linux actually it's a product of the hackers, right? The software hackers, they don't actually follow the hardware spec. But when we design the processor, wait, what's wrong? Wait, okay, so. When we when we designed the Diablo, we actually followed the spec from this is Spark read ISH. We got the verifications. We expect to follow spec. And one thing we found is for Spark, there's a processor state registered, right? But there's a 32-bit register, but some of the bits is for reserve, means for future use. Software shouldn't use it. But the current implementation with Spark processors, 32-bit Spark processor, they allow some of the reserve bits. This is writable and readable. And the Linux kernels actually use one of the bits to store really crucial information, like say to indicate whether or not the current processor in the OS kernel or application mode, that will be used to clean up the whole OS kernel stack. So we actually found we found out this bug purely based on luck, because we follow the hardware spec, but hackers, no, they have a machine, they just code for it. It works, it works. So also, if you look at Diablo, there were 6 FPGA systems that occupies half of the server rack, right? So this is a massive scale simulations. This is like a real machine. It's like think about number of DRAMs. You plug in the numbers from Google's number for software error rate for DRAM. You'll see real errors, soft errors in the system. We actually saw the DRAM errors, and also we saw errors from the SERDE links. We have lots of SERDE links, right? They are not 100% reliable. We see 1 or 2 errors for sure per day. Also, we actually this ends up to because we're using the memory in a different way, it ends up some of the nodes just die during the simulation. We think the FAME methodology on overall is great, right? This is it helps us on study problem at large scale, help us to get closer to the hardware side. And but we really think it's just need a really better tool to develop it. And now I code everything with the Verilog system Verilog, so I'm a system Verilog hacker. So I have to be frankly saying it's just not a very productive tool to build things. So we're actually working on second version. Maybe there's some DSLs can help us. Like say I'm a hardcore Verilog guy, right? Even I would say this is hard. So you have to think about whether or not you want to build a system just rely on Verilog. So again, Diablo is actually available from this website. You can go look for more information. And also we'll plan to publish all the source codes out there, and there will be paper upcoming. And I'm currently building the 2nd generation of Diablo hardware, and we'll talk about how we simulate 10,000 CPUs with enough memories in next versions. Okay, so with that, I'll be happy to take questions.
Any questions? So you said you tried to avoid all the IP from the FPGA vendors. Is there a particular reason you?
Yeah, they don't actually work. That's my frankest. Yeah, so like say the memory DRAM controller, they're not reliable enough. Once you have lots of clocks, clocking clock domains for science controller is not reliable enough. Besides, I don't like their controller because there are lots of hard coded like routing constraints in those things. And also the reason we design our own IP products, for example, the SerDes, right? You're not really using all the feature in the PCI Express. You're not using all the feature in the SATA drives. And also you want to make sure the whole thing is reliable enough. So we build our own retransmission schemes, reliable schemes there. And basically you can take it like TCP is equal to, or it's like a hardware TCP with window size equal to 1. And also for the control protocols, the Ethernet, right? Once you hook up lots of Ethernet cables to the servers, you'll see software running on the Axis server will drop the Ethernet packet. So there also must be some reliable guarantee and reliability guarantees in your hardware design. So you need to redesign the whole thing. It's not just like one, yeah. So you have to think about, don't grab off the shelf Xilinx, it will never work. I mean, for some people, but not for me. Yeah. Okay.
Any questions?
Oh, there.
Yeah, so you said that you had 128 megabytes per
Yes.
port, right? Does your target OS support virtual memory? Demand paging?
Yes, it's a full Linux. It supports anything support
So it
Linux.
supports the demand paging?
Yes, yes.
So
I just didn't turn it on in
didn't
this
turn
case.
it on?
Yeah.
Okay, but had you turned it on, you could, I mean, so is it possible that you could virtualize at the host level
Yeah.
to allow you to appear to have more than?
Actually, now we're building a second version. The second version will give you physically 4 GB per simulated servers. And the new server is not going to be single core model. It's going to be multi-core. And the idea is like you mentioned, we're going to use external flash as the main storage to provide you really multiple gigabyte DRAM storage and use the DRAM as the cache. So yes.
Okay, and then would you, in order to mean accuracy, would you stall
You stall.
You'll stall every
Assuming
time.
most of the time you keep the DRAM cache. And this is throughput optimized, the multi-threading design, so latency will be hidden, hopefully. And based on our current setup, like say I mentioned like 1,000 nodes, like 3 boards versus 6 boards, I don't see many actually raw performance simulation going down. So it's great. And besides the synchronization between the models, the high-level models run on different FPGAs. Since we control the protocol design ourselves, we've done that. The round trip time is like 1.6 microsecond, including all the payloads. I don't think you can do any. I don't think any of the existing parallel software simulator, parallel software simulator will beat that. And I don't see, to the best of my knowledge, there's an equivalent software simulator that allows you to do the same thing. Yeah. Question in the back? Or?
Well, I think you're going to talk to most of these people today,
Yeah.
so why don't we thank
Sure.
our speaker?
Okay, thank you.